Hello students, today we are with the portion electromagnetic induction and Faraday's law. Okay. So before getting on to the explanation, let us try to understand what is meant by this electromagnetic induction. Electromagnetic induction means whenever there is a change in magnetic field lines linked with a coil, a corresponding EMF is produced in the coil. Okay, due to which a current begins to flow in the circuit, and this phenomenon of production of an electric current using a magnetic field or varying magnetic field is called as electromagnetic induction. And the current which is produced or rather induced in the circuit is called as induced current, and the EMF induced is called as induced EMF. Okay, so before getting on to the basics or the theory portions, let's try to understand what is meant by electric flux. Okay, so electric flux is basically the number of magnetic field lines which is linked with a coil, or the number of magnetic field lines passing through a given surface. Okay, the number of magnetic field lines passing through a given surface is called as a magnetic flux linked with that coil. Okay, so this is the basic concept which you have to keep in mind. So now let's discuss about the experiment. This experiment consists of a solenoid. Okay, solenoid and a copper wire which is tightly wound around it, and it is observed that a galvanometer is being attached. Here you can observe that a galvanometer is being used, is attached to the circuit. What is the function of this galvanometer? The galvanometer is a device which is used to detect the presence of current. Okay, it is used to detect the presence of current. It is not used to measure the current. That's done by ammeter. The galvanometer will detect the presence of even a feeble current. Okay, we can convert this galvanometer into ammeter. Okay, nevertheless, we are not concerned about it now. Now our preliminary observation is that the galvanometer used in this setup is to measure, is to detect the current, whether there is a current produced or not. Okay, you can also observe that there isn't any battery or a cell connected to the circuit, so there is no chance that a cell can supply current in the circuit. Okay, so what when the experiment was conducted, it was found that here we have a solenoid. Okay, and this shows a direction of this shows a stationary magnet, okay, with the north pole facing the end A of the solenoid. Okay, so it was observed that when this magnet was moved near to the solenoid, as indicated in the diagram B, the galvanometer, which was earlier in the steady state means it was not showing any deflection, has now deflected towards the right, as you can observe in the diagram. Okay, so when the magnet was introduced near the solenoid, the galvanometer showed a deflection. Okay, the deflection produced by the galvanometer will indicate that there is an EMF induced, or rather there is the presence of a current. So we now wonder, from where has this current developed in the circuit? We have not connected any cell or battery to the circuit. From where did the current appear in the circuit? So let's try explaining it. Okay, so earlier when the magnet was away, we already know that the magnetic field lines originate from the north pole and terminate to the south pole, isn't it? So now when the magnet was away, the magnetic field lines passing through the solenoid was feeble or lesser in number. Okay, so while moving this magnet towards the solenoid, the interaction or the number of magnetic field lines interacting with this galvanometer increases. Okay, the number of magnetic field lines interacting with this particular solenoid increases. We have already defined what do you mean by flux. Flux means the number of magnetic field lines linked with that particular surface or the unit. So when I'm trying to move this magnet closer to the galvanometer, the number of magnetic field lines which is linked with the solenoid increases. Okay, so when the number of field lines linked with the solenoid increases, there is a change in flux produced. Okay, what do you mean by flux? Flux means the number of magnetic field lines linked with the coil. Initially, there was no association between the galvanometer and the field lines produced by this particular magnet. As we try moving this magnet towards the galvanometer, the number of magnetic field lines passing through the galvanometer increases. Okay, so there will be a change in flux. Initially, there was no magnetic field lines linked with the solenoid, so there the flux will be 0. Now, when I'm trying to move the magnet towards the solenoid, the number of field lines linked with the solenoid increases, so that the flux also increases. Okay, so there is a change in flux produced by this magnetic field in the diagram B. Okay, on the other hand, when after moving a particular distance, let's say that the number of magnetic field lines linked with this particular coil, when I tried to move this magnet into the solenoid, let's say that, for example, let's say that 10 number of magnetic field lines has got associated with this with the solenoid. That means for edge, I'm just taking a random example. Okay, let's assume that the number of field lines passing through this particular solenoid is 10. Okay, now this indicates a increase in magnetic field lines. Okay, initially there was no association between this magnet and the solenoid, so the number of field lines passing through the solenoid was 0 initially. Okay, now what I have done is I have introduced this magnet towards the galvanometer or the solenoid. Okay, so the number of field lines which was associated with this solenoid increases, and let's say this is 10. Okay, now after moving a particular distance, let's say that you are not moving this magnet anymore. That means there will not be a decrease or increase in the magnetic field lines, which was initially 10. Initially 10 number of magnetic field lines was linked with the coil in the figure B. Now if you are not moving it, or if you are not disturbing it any further, there will not be a decrease or increase in the magnetic field lines linked with the coil. Okay, so the galvanometer will not show any deflection. Initially when you try to move it closer to the solenoid, there was a deflection. Okay, and after moving a particular distance, if you are not trying to disturb the magnet any further, there will not be an increase or decrease in the magnetic field lines, so the galvanometer did not show any deflection. Okay, and what if you are trying to remove it? Initially in the figure B, you try to introduce this magnetic field or the magnet near to the solenoid. Now you are trying to move it away. So the magnetic field lines which we have assumed as 10, the 10 number of magnetic fields which was earlier in association with the solenoid has now decreased, because when you try to move the magnetic or the magnet away from the solenoid, the interaction between the magnetic field lines and the solenoid decreases, right? Initially this much association or relation between the solenoid and magnetic field was there, and if you try to move the magnet away, the interaction between the magnetic field lines and the solenoid keeps on decreasing, and now it was observed that the galvanometer, which was earlier deflected towards the right side in the figure B, will now deflect towards the left side. Okay, this shows that again there is a current developed. Okay, again there is a current developed in the solenoid. Moreover, the direction of current was opposite to the direction to which the galvanometer is deflected in the diagram B. Okay, so what can you conclude from this experiment? Okay, we can conclude that when you tried to move the magnet near the galvanometer, the number of field lines which was passing through the galvanometer increased. Okay, so there is a flux change. Flux change means initially there was no magnetic field lines linked with the coil. Now when you try to move it towards the solenoid, the number of field lines tends to change, or rather increase. So there is an increase in magnetic flux. On the other hand, in the experiment C, when you keep the magnet stationary, the initial number of magnetic fields, which I have assumed to be 10, is not going to change at all. The 10 magnetic field lines will never increase or decrease. That means that there is no change in magnetic field lines linked with the coil. That means the flux is 0. The rate of change of flux is 0. Initially, I assumed that 10 number of magnetic fields was linked with the coil, and if you are not trying to move it any further, the 10 number of magnetic field will remain constant. It is not going to increase nor decrease. Okay. On the other hand, if you try to move the magnet back, the number of field lines which was initially linked with this coil is now tending to reduce. Therefore, there is also a change in flux. Let's say that in the experiment B, we have assumed that 10 number of magnetic field lines was linked with the solenoid, and if you try to move it back, let's say that it has reduced and reached to 2 number of magnetic field. Now, there is only 2 magnetic field lines linked with the coil, so there is a decrease. Okay, so there is a decrease in magnetic field lines linked with the coil, so obviously there is a flux change. Okay, so what the experiment concludes is that whenever there is a rate of change, or whenever there is a change in magnetic flux or magnetic field lines linked with the coil, an EMF is induced in the coil. Okay, as you can see in figure B, there was increase. When you try to move the magnet towards the solenoid, there was an increase in the magnetic field lines, which resulted in a deflection in the galvanometer. Okay, and in the experiment D, when you try to move it away, the magnetic field lines linked with the coil has decreased. Okay, here also there is a change in the magnetic field lines linked with the coil. There also an EMF is induced. On the other hand, in the experiment C, when you keep the magnet stationary, the number of field lines linked with the coil will remain the same. Okay, so there will not be a change in the magnetic field lines linked with the solenoid, and hence there will not be an EMF induced. So what Faraday Faraday basically concluded is that he concluded that whenever there is a change in magnetic field lines or magnetic flux linked with a coil, an EMF will be induced, and this EMF is called an induced EMF. As a result of the induced EMF, a current starts flowing in the conductor, and this current is called as induced current. Okay, I hope it is clear now. The basic observations, the other observations are, if the magnetic compass or the magnet is in stationary, the galvanometer will not show any deflection. This is because the magnetic field lines associated with the solenoid are less or feeble. There is no association between the magnetic field lines and the solenoid, so there is no change in flux, and the galvanometer will not show any deflection because there is no current produced in the circuit. On the other hand, if you move it rapidly, if you move it towards the conductor, the magnetic field lines associated with the solenoid increases. As a result, the flux change there is a flux change produced, due to which the galvanometer shows a deflection. Okay, on the next hand, if you keep the magnetic compass stationary, then the number of field lines will remain the same. The number of field lines which has earlier entered into the solenoid will remain the same. It is not going to increase, neither going to decrease. So the rate of change of flux is zero. The flux remains the same. The magnetic field lines remains the same. There is no change in flux, and still the galvanometer will show no deflection. On the other hand, if you try to move it backward, the magnetic field lines which has earlier associated with the solenoid is now going to decrease. So there is a decrease in the number of magnetic field lines. Okay, so that now what happens is, there is also a magnetic flux change. Therefore, there will be an induced current, and the direction of this current will be opposite. Okay, here you can notice that the galvanometer will show an opposite deflection. Okay, the galvanometer will show opposite deflection. What happens if you move this rapidly? What happens if you move this magnet rapidly towards the solenoid? This galvanometer will show a rapid deflection. Okay, what happens if you remove this rapidly? This galvanometer will also show a rapid deflection, but the direction of deflection will be opposite to the direction of deflection which we have observed in the part B. Okay. So now let's try to find the direction of deflection. Okay, the direction of deflection of the solenoid or the galvanometer. See, in the figure B, we have introduced a north pole. Okay, north pole of the magnet towards the end A. So what happens is that when we introduce a north pole of a magnet, the end which is facing the north pole will also develop the same polarity. Okay, so in the part B, when we introduce a north pole of the magnet towards the end A of the solenoid will also develop the same polarity as north pole. Okay, since we know that both the like poles repel each other, the galvanometer or the induced current will try to oppose the magnet from entering into the solenoid. So the direction of induced EMF will be opposite. So here when we observe that the magnet is being introduced in this direction, so the EMF which is induced in the coil tries to oppose it back. Okay, so the direction of induced EMF will be in this direction. Okay, this is the direction of motion of the magnet, and the EMF induced will try to oppose the increase in magnetic flux which tend to produce the EMF. So the direction of motion of the magnet will be opposed by the direction of induced EMF. This shows the direction of the motion of the magnet, and this shows the direction of motion direction of the induced EMF. So the direction of induced EMF is such that it opposes the increase or decrease in magnetic flux linked with the coil. Okay, if the movement of the magnet tend to increase the magnetic flux linked with the coil, then the EMF will oppose. That is, the EMF will try to decrease the number of magnetic flux linked with the coil, and vice versa. Okay, here in this experiment, we try to move the magnet towards. Okay, so here we are trying to introduce a north pole of the magnet towards the end A. So the end A will also develop the north polarity. So since we know both the like poles repel each other, the EMF will try to oppose the movement of magnet into the solenoid. So the direction of induced EMF will be opposite to it. Okay. Now what happens if we try to move the magnet away from the solenoid? What if we try to move the magnet away from the solenoid? This end is the north pole. Okay, and the end A, which is facing the north pole, will develop an opposite polarity. Okay, north pole is now facing this end A, and we are trying to move the magnet away from the solenoid. So the end A will develop the south polarity. We already know that the opposite poles will try to attract each other. Okay, so the direction of induced EMF will be such that it tend to increase the magnetic field lines. We are moving the magnet in this direction. So the induced EMF will try to attract it back so that it increases the number of magnetic field lines magnetic field lines produced in the solenoid. So the direction of induced EMF will be just opposite. Okay, this is called as Lenz's law. Okay, the Lenz's law states that the direction of induced EMF is such that it opposes the cause producing it. Okay, let's explain in detail. So here, initially, the number of magnetic field lines increase was more. Now we are trying to move this away. That means the number of field lines linked with the solenoid is now going to decrease. So what the EMF does is, it tries to attract the magnet back towards the solenoid so that the decreasing number of magnetic field lines will tend to increase. Okay, so what the direction of motion, the direction of induced EMF is opposite to the motion of the magnet. If we move the magnet into the galvanometer, there is an increase in the number of magnetic field lines. So the EMF induced will try to decrease the number of field lines, and it will be opposite to the direction of motion of the magnet. Okay. Now on the other hand, if you try to move it away from the magnet away from the solenoid, the induced EMF will try to attract it back towards the solenoid. Okay. So that it develops an opposite polarity at the end facing the magnet. Okay. We already know that opposite poles attract each other and like poles repel each other. Okay. So now, this another important concept is that the Lenz's law is based on the law of conservation of energy. Okay, the Lenz's law is based on law of conservation of energy. Let's check how. Okay, so if we want to move the magnet from here towards the solenoid, we have to spend some mechanical energy in doing so. Okay, we have to spend some mechanical energy to move the magnet from the north, from this point into the solenoid. So there is a mechanical energy spent. According to the law of conservation of energy, energy can neither be created nor be destroyed. So the mechanical energy that we have done in moving the magnet towards the solenoid is now converted into the electrical energy, which is now produced in the solenoid. Okay, so the Lenz's law is based on the law of conservation of mechanical or energy, law of conservation of energy. Okay, so the main conclusions of Faraday's law are, whenever there is a change in magnetic flux linked with a coil, an EMF is induced. Okay, and this EMF induced is directly proportional to the flux change. If there is a greater increase in the number of magnetic field lines, the EMF produced will also be greater. If there is a lesser number of magnetic field lines linked with the coil, then the EMF induced will also be lesser. Okay, so we can actually write that the direction of induced EMF is directly proportional to delta phi by or d phi by dt. Phi is the standard representation of the flux, magnetic flux phi. Okay, phi is represented by magnetic flux is represented by the symbol phi. Okay, so the EMF is directly proportional to delta phi or d phi by dt. And if we consider the Lenz's law also, then we can suggest that EMF E is equal to minus of d phi by dt. Why this minus sign? Why this minus sign? Because we have already seen that the direction of induced EMF is opposite to the direction of change of flux. Okay, so this can be concluded that EMF is equal to minus d phi by dt or delta phi by delta t. Okay, so this is basically Faraday's law of electromagnetic induction. Whenever there is a change in magnetic flux linked with the coil, an EMF is induced. Okay, and the direction of the magnitude of induced EMF is directly proportional to the rate of change of flux linked with the coil. Okay. Now, what are the factors which affect the magnitude of induced EMF? It basically depends upon the rate of change of flux, and the second one is the number of turns in the solenoid. Okay, if the number of turns in the solenoid is more, then the deflection or the EMF produced in the solenoid will be more. And the Lenz's law. Next important thing is the Lenz's law. The Lenz's law states that the direction of induced EMF is such that it opposes the cause producing it. If the magnetic field lines tend to increase, then the EMF tries to decrease the increasing magnetic field lines, and vice versa. Okay. If we move the magnet towards, then the direction of induced EMF will be away. And if we try to move the magnet away, then the direction of induced EMF will be towards. Okay, I hope it is clear now.